Hello, mathematicians. This is Mr. Garcia, and today we got another lesson. This is lesson 8.6, which is about exterior segment lengths. So we're going to talk about segments that are on the exterior of the circle, which includes secants and tangents. So let's talk about our objective first. I can use the exterior segment length theorems to solve problems. So we're going to cover 3 theorems here. They're going to be a little bit confusing, so try to keep up. And each of these theorems deals with the lengths of some special segments involving secants and or tangents. So let's start with the first one. Theorem number 1 is tangent-tangent. What happens when I have 2 tangents? So let's take a look. If 2 tangents of the same circle intersect, so 2 tangents of the same circle intersect, then the length between where the tangents intersect each other and where they intersect the circle is the same for both segments. So what that's basically saying is between the point of intersection and the point where these tangents cross the circle or touch the circle, these segments right here are the same length, which means they are congruent to each other. So we can use this property to solve a couple of problems. Let's take a look at an example of how we use this theorem. So here I have a circle, and I can see that I have 2 tangents that both intersect each other in the exterior. So in order to solve this problem using our theorem that we just covered, first I need to find the segment of the tangent. Because notice that here, we're not using the entire line. We're only using the segment between where they cross and where they touch the circle. So I'm going to find those segments in this diagram. So I know that here is the point where the tangents cross each other. Here's a point where one tangent touches the circle. Here's a point where the other tangent touches the circle, which means that the segments I'm looking for are right here between those points. So these 2 segments are the ones that are congruent. So knowing that these 2 are congruent, I can find the value of x by solving an equation for x. Because I know that they're congruent, then that means whatever length this segment is and whatever length this segment is has to be equal. And because they are equal, then my equation is going to look like this. 5x minus 7 equals 17 minus 3x. So I need to solve this equation to get the value of x. Now we've done some solving already in the past couple of assignments, so I'm not going to go too in depth here because I'm sure you guys already know how to do this. So let's start by canceling the 3x. I'm going to add 3x to the side and I get 8x minus 7 equals 17. I bring that down. And now I'm going to cancel out the minus 7 with plus 7. And I do that on both sides. So I get 8x equals 24. And I divide both sides by 8 to get 3. So the value of x is 3. Now the next thing that they want me to find is the length of DE. So let's go and find the segment DE. Here's point D, here's point E, so the segment I want to find the length of is right here. Now, realistically, I could use either of these expressions to find that length since I know that they're congruent, so it would be the same thing. But just to keep it simple, I'll use the expression for DE, 5x minus 7. So I'm going to write that expression first, 5x minus 7. And because now I know the value of x, I can substitute that into the expression. So instead of x here, I'll plug in 3. So I get 5 parentheses 3 minus 7. So I have 5 times 3 which is 15. And so 15 minus 7 is 8. So the length of DE is 8. So this property is not too tricky, and it uses stuff that we've already seen, setting up equations equal to each other and then solving for x. So there's nothing really new here. So let's move on to the next theorem, which is theorem 2. Products of a secant with a secant. Now this theorem is going to be a little bit tricky, and you can see that there's a wall of text here. So I'm going to go through it and read as carefully as I can. Hopefully you'll understand some of it as we go through. So let's start. If two secants of the same circle intersect outside the circle, then the product of the length of the first secant's exterior segment and the sum of the interior and exterior segments of the first secant is equal to the product of the length of the second secant's exterior segment and the sum of the interior and exterior segments of the second secant. So there's a lot going on there. So let's break it down. We have two secants. In our example here, we see that one of our secants is FH and the other secant is KH. What this theorem is telling us is that if we break the secant apart into two segments where the breakup happens between the exterior part of the secant and the interior part of the secant, if we have those two pieces of the same secant, we multiply the outside segment by the outside plus the inside segment, and that's going to be equal to the same thing on the other secant. The outside segment of the other secant times the outside and inside segment of the second secant. Now you may have seen that HG plus GF and HJ plus JK are basically just saying the entire secant, the entire length of the secant segment. So another way to write this theorem is the exterior part of the secant times the entire length of the secant segment equals the exterior part of the second secant times the length of the entire second secant segment. Ooh, that's tricky to say without twisting my tongue. But basically, it means if I have the outside part times the entire length, that equals to the other outside part times the entire length. So yeah, it's a little bit tricky, but let's take a look at some examples. Hopefully that'll clear it up a little bit more. So here's the second example. And we're starting off by finding the value of x again. So according to our theorem, we need the outside parts of every secant and the inside parts of every secant. So I'm going to use some colors here to split them apart. Now I'm going to use two colors for one secant and two different colors for the other secant. So that way it's a little more clear where each part is going to go into our formula. So from L to G, well, first of all, let's identify where our secants are at. So I'm going to highlight this secant in red, and I'm highlight this other secant in green. So there's our secants. So now we need to identify the secant segment. I remember that what I highlighted here is the line because I'm including the arrows. But if I want the segment, then I'm not going to highlight the entire thing. I'm just going to highlight from where they intersect to the end of the secant. In other words, when it's coming out of the circle. So there's one of my segments, and here is the other segment. Now I want to separate the outside segment from the inside segment. So I'm going to reuse these colors here, and I'm going to identify the outside segments of each secant. So outside of the circle, there's one for one of my secants, and here is the other for the other secant. So that's pretty easy to find, right? The exterior part of every secant just goes from where they cross to where they first touch the circle. And that's my exterior segments. So now for my interior segments, interior, remember, is inside. So I'm just going to highlight the inside part of each secant. So starting from this point H to point K is one interior segment. And over here, starting from point G to point J is the other interior segment. So now I have identified the exterior and interior pieces of each secant. So now I'm going to go back and look at my formula to see how I'm supposed to set this up. So HG represents the exterior segment of one secant. So I'm going to start with one exterior segment of one secant, and let's use LH. So that's the red one right here. And I'm supposed to multiply that by that same part plus the interior part of that secant. So I have parentheses, because I'm going to multiply, and I have the exterior part, LH, plus the interior part of the same secant, which in this case is HK. Now, according to my theorem, this first part is equal to the parts from the second secant. So let's set that up. I have equals, I know something's here. So then I have parentheses here, and I have a plus sign in between them. So I know that outside the parentheses is going to go the outside part of the second secant. So LH was the first one. LG must be the second one. So I'm going to write LG on the outside here. And then I see that that's copied inside as well. So I'm going to write LG again on the inside of the parentheses. And then I'm going to put the part that goes inside the circle of that secant. So that's going to be GJ, right? That's the interior part of that secant. So here I'm going to write GJ. So now I have my formula set up. I've got all of my letters in place. So now I just need to substitute in the numbers that I have. So I'm going to start with LH. I know LH is 4, so I'm going to replace LH with 4. Same thing goes for this LH. And I'm going to put in my parentheses and my plus sign. Might as well do all this since I'm using black right now. Then I need HK. So I see that HK is 7. So I'm going to plug in 7 there. I move on to the right-hand side of my equation, and I see LG, and I know LG is 2. I can see it there. So I'm going to put 2 here, and LG is used again here, so I'm going to put that again. And then I'm going to put GJ, which is an expression, 3x plus 5. So I need to put in that entire expression. I'm not going to have room there, so let me erase this. And let me rewrite 3x plus 5. I'm going to put my parentheses back over here at the end. And so I have all of my numbers plugged in. So now all I got to do is solve this. Now I'm going to take this one step at a time though, because there's some parentheses here that are going to be playing tricks on us. So let's tread carefully here. Let's go one at a time. So inside my parentheses, I have 4 plus 7. And I know that 4 plus 7 is going to be 11. So then I have 4 times 11 equals. Over here, I'm going to keep the 2 on the outside, but on the inside, I have 2 plus 3x plus 5. So this expression is a little bit long, and I can simplify this because since I have 2 constants here, I have this 2 and I have this 5, I can combine those. So if I combine those, 2 plus 5 is 7. And then I have plus 3x. Let's continue simplifying this equation. The next thing I'm going to do is 4 times 11. I know that's 44. Now here, since I have a number on the outside of some parentheses, and inside the parentheses is more than one term, I need to distribute here. I need to use the distributive property. So I'm going to have 2 times 7, and then 2 times plus 3x. So 2 times 7, we know that that's 14. And then 2 times 3x, 2 times 3 is 6. And I'm going to make sure that I have the plus here, since this is positive times positive. It's still plus. 2 times 3 is 6. And this doesn't have an x, but this does. So I bring the x down with me. And so now I have my equation. So now I'm going to solve this. And I want to draw my line through here so that I can solve for x. First thing I'm going to do here is I need to see if I have x's on both sides. And I do not. I only have an x on the right-hand side here. So because of that, the next thing I'm going to do is move all my constants to the left-hand side. So that means getting rid of this 14. So I'm going to subtract 14. That cancels out. Over here, 44 minus 14 is 30. And on this side, I have 6x. The last thing I'll do here is divide both sides by 6. And so that leaves me with x. Sorry, my bad. X equals 5. And so the value of x, 5. So I've got my equation solved. The next thing they're asking me for is the length of LJ. Well, LJ is going to be the entire secant segment, the exterior and the interior. But now that I know the value of x, now I can find the length of the interior segment here. All I got to do is substitute in 5 for x here. So I'll do this over here, and I'm looking for GJ, right? So GJ is equal to 3x plus 5. I know that x is 5, so I'll substitute that in. 3 times 5 is 15. 15 plus 5 is 20. So that's going to be GJ. Now LJ, though, LJ is the combination of LG plus GJ. But now that I know GJ is 20, and I know that LG is 2, so 20 plus 2 is 22. So the length of LJ is 22. So yes, this theorem is a little bit more trickier, but since this is a video, you can rewind it, look back, look at the steps again carefully, and see what I did. And if you're still having trouble, then reach out to us. Let us help you. All right, so that's the second theorem. Now let's take a look at the last theorem here. Last theorem, I think it's a little bit simpler. So let's take a look at it and see if you agree with me. So first, the theorem is with products of a secant with a tangent. So now we have a secant and we have a tangent. Let's take a look. If a secant and a tangent of the same circle intersect outside the circle, then the product of the length of the secant's exterior segment and the sum of the interior and exterior segment of the secant is equal to the length of the tangent segment squared. So since we're already familiar with the parts of the secant due to the last theorem, we kind of understand this part a little bit better. We have the product of the secant's exterior segment and the sum of the interior and exterior segment. So that would be this part over here, the Lm times Lm plus Mp. We see that Lm is this exterior part and Mp is this interior part. Now what's different here though is that since the next segment is a tangent, that is just the tangent, the length of the tangent segment squared. So whatever this tangent measures, we square that, and that's what we're going to use for this side of the equation. Now, as previously, the secant, since Lm plus Mp is just the total length of the secant segment, we can simplify that formula to be Lq squared, the tangent section, equals Lm, the exterior secant, times Lp, the entire secant segment. So again, we're using a lot of letters here. We're using a lot of big words. So let's take a look at an example to break down what we have to do to use this theorem properly. So here's our example. We're looking for the value of x again. And just like how I started the secant example, I want to start off here by identifying the interior and exterior segments of the secant first. So let's go and highlight those. Now, first I need to identify my secant. Remember that the secant is the line that crosses the circle 2 times. So here's the first time, here's the second. So this line will be my secant. Now that I know which one my secant is, I want to break it apart into the exterior and interior segments. So I know that the exterior obviously is outside, and it only goes up to the point of intersection, point Q here. Then the interior part would be inside the circle from point P to point N. Now the tangent is just going to be from point Q to point M, because that's where it intersects the circle. That's where it touches the circle. So I'm just going to highlight that part. So now that I've identified my segments, I want to know where the values of those lengths are going to go. So I'm going to look at my theorem again. I'm going to look at the formula. And we have LQ squared is our tangent. So let's start with that. Let's start with our tangent here. Our tangent here is QM. So we're going to start with that length. And the length of that is 6. So I have QM squared. And I know that that's going to be 6 squared. And then I'm going to have equals, and let's see, equals Lm, which is the exterior part of the secant. So the exterior part of the secant here is QP. So that's what's going to come next here. So QP, and we know that QP is 3. So I'm going to put 3 there. And then I know I'm going to have parentheses and then plus in here. Same thing here, but I'll wait on that part. Let's go back to our theorem, see what's next. So we have Lm times Lm again plus Mp. And Mp is the interior part of the secant. So I know I'm going to have Qp again, since that's the exterior part. But in the interior, I'm going to have Pn. Now the corresponding values for those, Qp is 3 and Pn is x. So I'm going to put x over here. And so there's our formula, there's our equation. So now we need to solve that. So let's start with our 6 squared. 6 squared, we know that's going to be 36 equals 3 times the quantity 3 plus x. So again, because I have that number outside the parentheses and multiple terms inside the parentheses, I need to distribute that 3 to each term inside the parentheses. So 3 times 3 is 9. 3 times x is going to be 3x. And I put plus here because it's positive 3 times positive x, so it remains positive. So now I'm going to solve this, and I'm going to draw my line here. And I start by looking at both sides to see if I have x's. And I only have an x on the right-hand side, so the next step is to look for constants. And I do have a constant on the right-hand side, so I need to cancel that out. Since it's positive 9, I subtract 9 from both sides, and that's going to give me 27 over here. And on the right-hand side, I'm only left with 3x. And so the next thing is to divide both sides by that 3 to cancel that out. And so x is equal to 9. The value of x here is 9. Next thing they're asking more is for the length of Qn. So the length of Qn is going to be this 3 plus whatever x is. But now that I know that x is 9, I have 3 plus x, which is just 3 plus 9, and that gives me 12. So the length of Qn is 12. This one not too bad, right? At least not as bad as the secant one. But it does have its challenges, which I'm going to talk about in the next example. Now this example, as you can see here, applies only to pre-AP and dual language. So if you're in regular geometry, you don't have to worry about this. Yay, go do your homework. But pre-AP and dual language, stick around because this is going to help you out. And of course, if you want to stay here and watch it just because you want to learn and be smart, you can do that. So let's go and solve this. Now again, what I need to do first is I want to look at my theorem, and I know that I'm going to have the tangent squared first. So I'm going to look for that tangent segment here. And so I look at this line, and this line is the secant, so I'm not worried about that right now. Up here, AB is my tangent, and I can see that because I have the point intersecting the circle and the point where the lines intersect. So there's my tangent segment. Now I want to identify the interior and the exterior parts of my secant, my LM and MP. So let's go find, I know where my secant is now. So I'm going to highlight the exterior segment of the secant in red, and I'm going to highlight the interior segment of the secant in blue. So now that I have all of my segments marked, now I'm going to follow my theorem and plug in my values. So I have LQ squared first, that's my tangent. So I have my tangent, which is 3x minus 2. And I'm going to go ahead and write them on the top here, so we're following the theorem properly. And I have 3x minus 2 squared. And that's going to equal LM, which in this case is the exterior part of the secant. Oops. So the exterior part of the secant is AC, which is 2x minus 12. And I'm putting that in parentheses so that I know that that's going to be the expression for the exterior part of the secant. Let me put his here. And I know that there's going to be AC again because now it's the exterior part plus the interior part, which in this case is CD. So I have the exterior, which is again 2x minus 12, and then plus the interior part, which is positive 6. And so there's my equation. Using our theorem, we've got our equation now. And boy, is it a doozy, huh? Let's simplify what we can here, because I'm going to show you a little trick. So I'm going to keep this as 3x minus 2 squared. And over here, I'm not going to worry too much about the coloring. I have 2x minus 12 for my exterior segment. Now inside the parentheses, I can simplify this part over here because I have constants. So I can combine those constants to simplify my equation a little bit. So that's going to become 2x. Negative 12 plus 6 is minus 6. Now, in the previous homework, we did have you guys factor these quadratics. But as you can see, they are getting a little bit difficult. And plus, in today's age of technology, why would you need have to factor quadratics by hand? Now, this is not saying that you shouldn't know how to do that. Obviously, it has its purposes. But I'm going to show you on my phone now how you can just factor this on a calculator and where you can get that calculator from. So to find x, using a graphing calculator. Well, first I need a graphing calculator, so I'm going to open up my Desmos apps here. And you can download this, or you can use the website as well. You can also do it on the computer. It's the same steps on there as well. So what I'm going to do is we're going to type in our two equations into the calculator and see what the graph looks like. So let's start with our first one, which is 3x minus 2 squared. And I press enter. Now I'm going to type in my second one. So I have 2x minus 12, close parentheses, open parentheses, 2x minus 6, close parentheses. And now I'm going to go to the top half of the screen here, and using my finger, I can drag this up. And if I click on one of the graphs, either one of them, then it'll show me some of these points in gray here. And if I go up here, there's a point in gray there. And that point is where they intersect. So if I highlight it here, that's the point that we're looking for. And if I click on that point, it tells me the coordinates 2, 16. So here we know that x is going to be 2 and our y is going to be 16. But the important part is that we have that x. Well, that was easy, right? Turns out that x is equal to 2. So now that I know x, and I know the value of x, I can find the length of AB and the length of AD. So why don't we start with the length of AB first, and that's going to be our tangent. So AB is equal to that 3x minus 2. And I don't need parentheses, so I'm just going to write it in here. 3x minus 2. Now I'm going to substitute the value of x. That gives me 6 here. 6 minus 2 is 4. So the length of AB is 4. Now the length of AD, we need to add those, right? But we also remember that this part is AD because I added the exterior and interior segments. So I'm just going to use that. I have 2x minus 6, and that's going to be for AD. And I substitute my value of x, which for some strange reason is going to give me a negative answer. That shouldn't happen because obviously, how can a length be negative, right? But the important part here is that the steps for your problem are going to be the same, and you shouldn't get a negative answer because, of course, how can this length here be negative? There's no such thing as a negative length. So in your homework, you will get a positive answer. Well, this is embarrassing, but oh well, no big deal here. All right, well, that's the end of the lesson, guys. If you have questions, again, remember to reach out to us. Let us know you have trouble. Text us on Remind. Let us know on Google Classroom. Yeah, so I'll see you guys next time. Take care.